The other version of the Clausius-Clapeyron equation that we want to use is what is called the 2-point form. This form completely bypasses that factor A. Okay, and this form is going to be the most useful when given two sets of pressure temperature data. Hence why it's called 2-point, right? So you have the version on your sheet, okay? This equation comes from that linear form, setting two equations both equal to A because A is a constant for the compound no matter what it is. There are multiple ways you could find this equation on the internet, okay? This is the way our book gives it, so this is the way I'm giving it. Natural log of your second pressure data point. So we're going to have a set 1 and a set 2, right? P2 over P1 equals delta H. Now notice in this version that we are using, the negative sign is no longer there in front of delta H, right? It was over here. It's not here. Divided by R times 1 divided by T1 minus 1 divided by T2. And there's our form, okay? This is a plug and chug formula. This is more algebra to rearrange though. And you've got this natural log that you may have to take care of in some places. So the algebra on this is a little more tricky. And if algebra is not your strong suit, I encourage you to come get with me, maybe during lab time today, and let me show you how my kind of shortcut, easy trick to rearrange these equations. Okay. But algebra is a prereq for this class. And so I do have to assume that you can rearrange this equation. And if you just need the extra help, then you come find me after class. Okay. So all we're doing is plugging in and solving for a variable that we do not know. I will say that, let's remember in your data sets, right? In your data sets, okay, your pressures can be any they can be any units, but they have to be the same unit. Okay. They could be kilopascals, they could be atmospheres, but they got to be the same. And of course, as always, temperatures must be Kelvin no matter what. Okay. So let's look at an example. Let's look at number 6. Carbon tetrachloride. Okay. Here's my question for you guys. Look at that compound, carbon tetrachloride, CCl4. Is that polar or nonpolar? Okay, you are correct. It is nonpolar. And you're like, but it's carbon and other things. Is it carbon and hydrogen and other things? No, it's not. It's just carbon with 4 chlorines around it. Is that symmetrical? Yes. All the dipole moments are pulling equally. It's all canceling each other out. That's nonpolar. Okay. What are the data sets? Let's pull out. What do I want to see when you guys have a question like this on a test? What do I want to see is show your work. Pull out your data sets that you're using. What's one of the first pressure temperature data sets that you observe when you read through the question? Give me one.
The pressure of carbon tetrachloride is
okay.
54.0.
54.0 kPa.
At 57.8 degrees Celsius.
Okay. Right away, 57.8 degrees C. Guys, right away, go ahead and change that to Kelvin right now. Celsius plus 273.15. Do it right now. Okay. Who is on my phone? Oh, I already know the answer. I already know who's doing it. So if we're going to round it to 1 decimal place, to the tenths place, then I got 331.0. Yeah, I got 331.0. If you choose to not round it yet and you take it out to 2 decimal places, it's fine. It's fine. Okay. What's the other set of data? We've got a pressure. Ooh. What's the pressure here? It doesn't say it explicitly. What does it say? Normal. It says normal. What is normal pressure in kilopascals?
101.3.
That's what you got to know now. That's part of your knowledge now. What is the normal boiling point? What is the temperature at 101.3? What's the normal boiling point? And I did not say this. Will you guys add this to this question? I do want your answer in degrees C. So you're going to find it in Kelvin, and then you're going to have to subtract and give me the answer in degrees C. Please add that to that. I do want this in degrees C. Okay. What else did I give you? I gave you the enthalpy vaporization. 33.05 kilojoules per mole. Does it matter what set you call set 1 and what set you call set 2? No, it does not matter. You show me which one you're calling set 1 and set 2. When you are writing this down as part of your show your work, okay? What do y'all want to call this set? You just want to say 1 because it was the first one? Let's do that. That's fine. You be sure you show me on your work. You're like, okay, this is my P1, Miss Poe, and this is my T1, Miss Poe, okay? You show me that. So then that means this is my P2, and T2 is what I'm solving for, yes? In your equation. And so then I would want you to write, you can write just this equation that you're starting from, or you can go ahead and write me the rearranged one. Either way. You can show me, I know I'm starting with this equation and I'm solving for T2. I do want you to show me your rearranged equation. Because I need to see that I don't need to see the steps you got there, but I want to see your final rearranged equation. I want to see the rearranged equation. So again, you don't have to write this original version for me unless you just want to. What do I want to see? Rearranged. Can you guys algebraically rearrange that equation for T2? I thought this is a little tricky. It's a little tricky. I do have I guess it's not really a shortcut. It's kind of, I don't know. Again, if algebra is not something you're real good at, come see me during lab time and let's go through it together. But here is the rearranged equation. Okay. One over T1 minus natural log P2 over P1 divided by your delta H of vaporization, that is divided by R. And then this whole answer is raised to the -1 power. What does to the negative 1 power mean?
1 over.
It's the inverse. It's the reciprocal. Yeah, it's the that's what I should say. It's the reciprocal. It's 1 over this answer. Abigail's like, okay, that's it.
Yes.
So we don't have delta H valve, do we?
Yeah, I gave you. It was given to you in the question.
What?
It was at the end of the sentence.
Oh, okay.
Yeah. And so from here, now, actually, which I'm not trying to confuse you, but what could you do with this R value instead of having this R on the bottom of your fraction? Where does that mean this R actually is?
On the top.
It's up here. I mean, whatever. That's fine. That's true. That's also correct. That's fine. Whatever. Try not to add more confusion to the situation. Okay, but so now it's plug in and go. Plug and chug. Plug in your numbers. If you need to break it up piece by piece, if you don't feel comfortable typing it all into your calculator at one time, okay. 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 But I'm going to give you a minute. I want you to plug in and solve for this answer, T2. Break this up however you need to. If you feel comfortable plugging it all in, if you got a fancier calculator where you can really see it laid out just like this, that's what I would absolutely do. So I just put it all in at one time. If you're using a simpler scientific calculator, you may want to piece it out. I don't know.
On a 284, how do you, never mind, I found it.
Okay. And then don't forget at the end, after you've gotten this answer, you have to raise it, do the little caret, right? Raise to the negative 1. That's taking the reciprocal of it. Okay, after you get all this math done. Okay, I'll be right back. This will give you all that minute you need to plug it all. This is the answer I've written up on the board that I got in Kelvin when I solved for T2. Within a decimal place or two.
Holy moly. I forgot the exponent.
Okay.
I was like, it was really small and I was very confused.
Don't forget to take it, raise it, do the reciprocal of your answer. One, you can either hit 1 divided by answer, or you can take it and do caret negative 1. Okay. Let me see. It is. That's why you might rather piece it out. So maybe try, if you got it written out, just do one little number set at a time and then combine it all together. So
Right, how I'd rather on the calculator.
okay. Again, this is something we can maybe work through more in the lab afterwards and help type it in. Okay. So this is absolutely, especially for you guys who haven't had me before, where partial credit comes into play, right?
Yeah.
Right? If you show me, Ms. Poe, I knew these were the right numbers to use. And Ms. Poe, I even rearranged the damn equation correctly. But I did something funky when I can see from your answer, something when you typed it in your calculator didn't go right. That's, to me, that's almost full credit. You did all of that correctly. That's almost full credit. So it is super important to show me what you can so I know you understand what you're doing. Okay? So did you end up with that?
Yeah, no, I got that.
Did anybody else get to this point? They got this number? That's excellent. That's excellent.
Correct for where the negative exponent was.
Uh-huh.
I had to make sure it was fully outside of
every other thing. Yeah, okay. So again, this takes some practice.
Yeah, I had to put 1, 2,
Right.
3, 4, 5.
This takes practice.
8 parentheses.
I'm trying to remember the natural log calculator thing.
It should be that same button where that little E was. No, but you should be using LN, not E. So don't hit second and then that number, just do LN. Just hit LN.
Yeah.
So it is not log. Log is base 10, right? You're actually doing natural log. You're hitting the LN button. Okay. All right, so what's the last thing you need to do though?
Convert to Celsius.
This is not the final answer I want. I want this answer in Celsius. Minus 273.15. Depending on how much you rounded and where you rounded, you might get 76.2 or you might get 76.1. If you're somewhere in that ballpark, you are correct. Okay. Guys, these are going to take you a lot of practice. That's why this first set isn't due, and this first homework set is not due until Thursday. Okay. Let's do one more CC equation together. I've got a third one that the solution should be worked out on the slides. And then we need to go ahead and talk about this last topic of this section 10.3. We have to finish this section today to stay on schedule. So, if you do go look at my slides, right, these lecture 1 slides, if you do go look at these, and you're into, it's almost toward the end of them. All right, here is that question we just worked, okay? And it shows you the rearranged version. Here is the next one, number 7, where you are solving for delta H of vaporization. This is not the one I want to work with you because this answer is basically here, okay? And there's your 2 sets, and you just have to rearrange your equation to solve for delta H. Again, I can give you a little bit of a trick for that. The one I want to work with you is the one where I have not had time to put any information on the slide. So this is number 8. Okay, that's the one I want to work together right now. Let's work number 8. Acetone. CH3, 2, CO. What do you think acetone is? Is acetone polar or non-polar? Absolutely. What kind of IMS does acetone have, do you suspect?
All of them.
Can it hydrogen bond, though? This is information is coming, but let's look at where that oxygen is. Does it appear that that oxygen has any hydrogen
Sorry,
attached
carbon
to it?
formed the hydrogen, so.
Yeah, this compound actually looks like this. Nope, that's not what I meant to draw. That's what that compound looks like. So it's polar because there's a pull there, but it can't hydrogen bond. So it's just has LDFs and it has dipole-dipole attraction, and that's it. Okay, that's not the point of this problem, right? What's the point of this problem? The normal boiling point is 56.5.
So that means it's the boiling point at the 101.3.
Yep. Or what's up? What else is normal? 1 ATM, right? Did I specify in this problem what pressure units I wanted you to use? I didn't specify. I would in a question. I guess we'll do it in kilopascals. That's cool. Normal boiling point temperature 56.5. What is that right away in Kelvin?
329.65.
Right away. Always just right immediate, automatic. Right? Now change it to Kelvin. What is the vapor pressure? So I'm obviously looking for my other P value. Okay, I'm looking for another P value. What is the vapor pressure at 25 degrees C? That's 298.2 Kelvin. Which set do you guys want to call set 1 and what do you want to call set 2? Again, it does not matter, but think about what you're trying to solve for. You're solving for one of your P's. When you look at that equation, when you look at this equation, and you're wanting to solve for one of these, which one is the easier one to solve for? The top, always the top. You don't have to think about inverse, reciprocal, blah, 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 blah. Well, let's solve for P2. Let's make our data set solve for P2. So that means I'm going to call this set 1, and I'm going to call this set 2. That's the smart move. So again, this is, I want to see this. I want to see that what you are using for your data sets. Yes. You can write down the delta H of vaporization for yourself. I don't need you to because it's right there in the problem, but if you want to, that's fine. Okay. And now give me that rearranged, if you need to rearrange it. What's going to be the easy thing to do because we're solving for a pressure? Man, it's already set up to solve essentially for one of these pressures, right? Isn't it? Okay. What do you need to do, though, in order to get pressure out of the natural log?
E to the power from what it's
You have to take the inverse log, the inverse natural log of both sides. So if this is the equation you start from, the action of raising both sides to E, right, does what? Gets rid of that natural log. So now you have a fraction. You have P2 over P1 equals E raised to all of that mess. Raised to all of that. This is a very common notation to use, guys. If you don't want to try to write it all up here, something that is very common is just to do E, and then you can do caret sign raised to, and then just write it all in a bracket there next to it. That's fine.
All of that times P1.
Yeah, because what would be the last thing you need to do algebraically to get P2 by itself? Multiply both sides by P1. Again, I'm actually kind of working this math out for you right now, right? Really, what do I want to see, guys? I mean, you can show me all this, but what do I really just need to see at the end of the day? Your rearranged equation. So your rearranged equation should really look, I mean, however you write it is however you write it, but it should really look something like this. P2 equals, because remember, this P1 is not part of the exponent, right? It's its own. So I'm going to write it like this. P1 times E raised to the delta H of vaporization divided by R times 1 over T1 minus 1 over T2. And now it's plug in your numbers and give me the answer time. Are y'all like, oh my God, I didn't realize this was going to be like this? The algebra? Y'all okay? Okay. I got something around that, 30.3. Make sure you remember to use the 8.614 times 10 to the third value for R. 8.314 times 10 to the negative third. Okay.
I got 24.4. Seems a little off. Oh, 31.
So you got closer to this?
Yeah. I'm gonna check my calc.
No. I mean, I do, but maybe not right this second.
Okay.
Is that cool?
Yeah.
Okay. Again, if it works for you, I don't often say this, but if it works better for you to just kind of like do, hey, what's this value? What's this value? Let me do E raised to the, I mean, that's fine, you know. No, it's 30.3. Yes, it's 30.3. Okay. But I can check anybody's calculator entries and all that stuff when we get down to lab. Last topic, a heating curve, phase transitions. So we're still in section 10.3, okay? But we're actually starting a new set of lecture slides now. So we're going to our lecture 2 slides, still in chapter 10. Okay. So what I would like for you to recognize is that, you know, when you have this phase transition, solid to liquid, right? We already know what this is called. Solid to liquid is called what? Melting. Do you know what we call the enthalpy change that is associated with that? You know, we were just talking about delta H of vaporization, right? For when you vaporize. What do you think this delta H is called for when you're melting? No, like what's the little abbreviation that goes down underneath it? Like over here, we were saying delta H of VAP for vaporization. What do you think this is?
Melt.
And you would think that, wouldn't you? But it's not. It's not called delta H of melting. It's called delta H of freaking fusion. I don't know why. Okay. That's what it's called. I know. Aren't you angry about it, Yuriema? It's called delta H of fusion. The melting process, the enthalpy added in is called fusion. It's called fusion. But again, it is going to be what? Positive, right? Because it's an endo process. So what is the reverse called? Okay, this is called freezing. And this delta H is called delta H of freezing. Okay, yes, yes. You will not often see this, though. You will only be given, God bless you, delta H of fusion for a compound. Did y'all hear me? No, because Yuriema was sneezing. You will not often, or I would say ever, just be given delta H of freezing. You just won't be given it. You'll be told delta H of fusion. That's the standard value you're given. What do you know, though, must be true about these two delta H values? Think first law of thermodynamics. Energy can never be created or destroyed. It's only transferred. If it takes X amount of energy to melt, how much energy does it take? How much do you have to remove to freeze? X. Equal value, opposite signs. So the delta H for this process would be equal to negative value of your delta H of fusion. You need to keep that in mind. Equal but opposite. Equal but opposite for that. Those opposite processes, equal value, opposite sign. Equal value, opposite sign. What about liquid to gas? Again, we already know that going from liquid to gas phase is called vaporization. And we've been working with that enthalpy, delta H of vaporization. And that number is a positive number. What is the reverse opposite process called? Condensation. Yes. But will you ever be given, similarly to here, will you ever actually be given a delta H of labeled condensation? You're not going to be given that. What do you have to know in your head now? This value equals what?
Negative delta H of vaporization.
Absolutely equals negative the delta H of vaporization, which you are given all the time. You're given that value all the time. And then, like I said, we're not really going to worry too much about sublimation and deposition in this process because what we want to look at are these more standard phase changes. So I want you to recognize and remember something about calculating heat. Do you guys remember one of the equations, or any equation that you learned in Gen Chem 1, how you can calculate how much heat is added or removed from a substance? The MCAT, that's the one I want you to remember. Okay, so here is your first big way to calculate heat. When you have a substance that is heating or cooling, a substance is heating or it's cooling. And when a substance is heating or cooling, it is in a single phase at the time. I can heat water, I can cool water. You're in a single phase. The heat added or removed, depending on what you're doing, right? If you're heating or cooling, the heat added or removed increases or decreases, as the case is, increasing or decreasing the kinetic energy. What does that mean? Kinetic energy means what? Motion, movement. Motion, movement. Kinetic energy, motion, movement. If you're adding heat, you're increasing the kinetic energy. What will you see happen to the temperature? Increase, yes? Okay, what if you are removing heat from a substance? What's happening to the kinetic energy?
Getting lower.
Slowing down. What happens to your temperature?
Decrease.
Decreases. Here's the main thing. You see a change in temperature. You will have a change in temperature in this situation. When you are heating or cooling something, you are changing the temperature. Yes? So what equation would you use to calculate heat when you have a temperature change? Q equals MCAT. And if you don't remember what MCAT, all of those variables stand for, it's on your sheet. Heat equation to use when the substance is heated or cooled. Q equals MCAT. And it tells you right there what all of those variables mean. Here's what's new to you guys. When substances are in a phase change, I do not mean they are being heated or cooled. I mean when they are literally going through their phase change. There is no change in temperature. Did y'all know that? Did you know that when you're melting ice, as the ice is in your hand melting, if you had a thermometer in there, the temperature of the ice, and then the ice water mixture, and then finally just the plain water would stay 0 the whole time until all the melting has been done. After it's all liquid, after all melting has been done, and you continue to hold it in your hand, what will happen to the water? It'll continue to heat a little bit because now your hand's freaking ice cold. But it would still heat up some, right? But during the actual phase change itself, there's no temperature change, you guys. All heat added or removed goes into breaking or forming those intermolecular forces. There is no change in temperature until that is done. So how much heat does it take to phase change? This is how we calculate that. Heat equals N. And what do you think N is? If M is mass, N is moles, because it's National Chemistry Week, times the delta H for that phase change. Moles, delta H. I think I'm going to wait on that. I think what I want us to do right now at the end of class is I want us to just let's sketch what's called a heating curve. And then we'll pick up with this tomorrow. So I have this on the slide. I have a heating curve for water, but I would like for us to sketch it together, okay? So when we talk about a heating curve, what I'm wanting you to plot is a XY graph. On the x-axis, on the y-axis, I want you to plot temperature in degrees C. And on the x-axis, a heating curve means we're plotting the amount of heat or energy, what, added or removed. If we're heating something, are we? Okay, so on this, we are adding heat, heat added. Okay, that could be different if it was a cooling curve. It would be heat removed, but this is heat added, okay? Let me try this, guys. That better? Yep. Okay. Start from, again, we're doing for water. Show me the 3 phases of water. Show me solid, going to liquid, going to gas. Okay? So if I start with water as a solid, and it's in a single phase, what should I see happening to the temperature as I add more heat? If I have just ice and I'm just heating it in my hand, what happens to the temperature of the ice? Okay, when it's solid, it's increasing. What does that look like on a graph that plots temperature versus heat added? It looks like an increase. Yes? My solid, as I add more heat, the temperature of it increases. Everybody good with that? Until it hits a certain point. What do we call the point when it phase changes from solid to liquid? Melting point. This solid will increase in temperature until it hits its melting point. Until it hits its melting point. For water, what is water's melting point?
So 0 degrees.
0. So label that. For water, tell me what the temperature is. You know what it is now. What is it? 0. Okay, and so now that it's at 0 degrees C, what phase change will happen? What do we call the phase change when it's going from solid to liquid? Melting. Okay, and what did I just teach you? During a phase change, there is no delta T. So if I'm adding heat, but I'm not increasing in temperature, what does that section of this graph look like? A plateau, a flat line. And I'm not asking you to be accurate with how much or how long your lines are. That's not the point of this. This is just a sketch. So this would represent the phase change melting. Yes? And when it's melting, don't you have both solid and liquid at the same time? Think about in your hand. When the ice is melting in your hand, don't you have both phases at the same time? They're both there at the same time. What's the delta H called for that? It's the weird one that we just learned. Fusion. Delta H of fusion. Okay. So think, for this portion of the graph, right here, how could you calculate how much Q, how much heat was added for this portion right here? What equation would you be using if you're calculating where you have a single phase that's changing temperature? If you have a delta T, which
MCAT.
equation are you using? MCAT. You are in a single phase. You are calculating Q with MCAT. Because you do have a delta T, don't you?
Mm-hmm.
If you're at a phase change, though, how do you calculate? How do you calculate Q? You don't use MCAT, you use NA. NAS, huh? Right, that's what you would use there. Okay, so let's say the phase change is complete. All the water, all the ice has been melted. I now have liquid water that I'm holding, or that's in my jar. Because my hand is like literally freezer burn now. Okay, frostbite. If I keep adding heat, what happens to the liquid?
Condenses into gas.
No, you have liquid and you're adding heat. What's happening to the liquid? You're just increasing the temperature. As you add more heat, the temperature of your liquid increases. So what does that look like? Another slanted line. This is your liquid. Until you reach what temperature?
100.
For water, it's 100 degrees C. But what is that temperature called where you stop being a liquid and you start turning into a gas? What do we call that temperature? Boiling point. Excellent. For water, it is 100 degrees C. For any other substance, I'd have to tell you what it is. Water is the only one you should absolutely know. Okay? What's going on here? We call that vaporization, yeah? We have liquid and gas at the same time, boiling above the surface of the water. If I'm just in the liquid phase and I'm heating it, what equation would I use to calculate how much heat was added? MCAT. But if I'm here and I'm in a vaporization phase change, I would calculate Na. Using which delta H? Vaporization. Use the one for your phase change. And then shoot, I could take that gas now and I could keep heating it.
Up in the plasma.
Yeah, I mean, you could heat it, you know. I have gas here. Again, if I needed to calculate how much heat was added to the gas phase, what equation would I be using for a gas? MCAT. We're going to work through calculations with these steps tomorrow. Yeah, tomorrow. So we're going to work through these tomorrow. I'm going to ask you to calculate how much heat it takes to take ice from negative 15 degrees to steam at 120 degrees. I'm going to ask you to calculate that entire amount of heat. I'm going to give you all the data. You have to know there's this step, this step, this step, this step, and then this step. Jesse? Oh, I thought you were raising your hand. You had a question. Okay. All right, guys. I'm sorry today was so long. I didn't really intend for it to be. I don't quite know what happened. Everybody get logged into ActiveChem okay? I hadn't actually checked yet. Does anybody have an issue so far? Or okay, let me know if you do. Go ahead and, if you haven't, absolutely get logged in today. We're going to go down to lab, work on titration, if you need to finish that. And this is your time to ask me calculator or algebra related questions to this topic. The lab we're doing tomorrow is a dry lab. It's a graphing lab over graphing phase diagrams. But I still want you to read through the instructions beforehand. So be sure you have grabbed your copy of that lab down there to read through beforehand. Who has a laptop that has Excel on it? And I don't mean that stupid free student version of Excel. Okay. 1, 2, 3, 4, 5, 6. Okay, we should be okay. I think I have enough. If you will be sure you have yours. I think I have enough laptops for everybody tomorrow to graph appropriately. I got one more thing for you to do tonight. Study section 10.5 on your own. So I asked you to study 10.2, those liquid properties on your own last night. I want you to study section 10.5, types of solids tonight. And I made a video for you. I got to upload it to YouTube. It's a 10-minute video, and I walk you through the 4 types of solids I want you to know. I will put it into the chapter 10 folder on Blackboard. I'll put the link into the chapter 10 folder on Blackboard. Okay. It's a 10-minute video. It's 4 types of solids. I want you to know some properties of each one. Okay. Study that tonight, and so then we'll be ready for class tomorrow. Okay. All right. Let's get down there, and hopefully you can get your titration lab finished today and turned into me today. That's the goal. If something happens and you need an extra day, that's fine, but the goal is to get it done today.